Okay, then we get the number of moles here of hydrochloric acid given the new volume but the same concentration. So mole of hydrochloric acid is equal to 0.025 cubic decimeters times the concentration, which is 2.0 mole per cubic decimeter. So this is 0.050 mole hydrochloric acid. And then for the volume of sodium hydroxide in the second experiment is 50 cubic decimeters, so that is just 0.050 cubic decimeters. Then we can get the number of moles of sodium hydroxide, so that is 0.05 times 2, that is 0.10 mole. So now take note here that they don't have equal number of moles to complete neutralization. And hydrochloric acid here is less than, right? The number of moles of hydrochloric acid is less than that of the number of moles of sodium hydroxide. So that means hydrochloric acid here is the limiting reactant. Since it has only 0.05 mole to neutralize. Okay, then now let's compare the heat released. Maybe I should take the... Oh, it's gone. What happened? Okay, we've already calculated the number of moles in the second experiment, and then we found out that they don't have equal number of moles for hydrochloric acid and sodium hydroxide. And hydrochloric acid here is the limiting reactant, since it has only 0.05 mole that neutralizes the reaction. So let's compare the heat released here. So the heat released is directly proportional to the number of moles neutralized. So in the first experiment, the change in temperature is 13 degrees Celsius. In the second experiment, okay, notice here that we only got 0.050 mole, and for the first experiment it has 0.10 mole to complete neutralization. But for the second experiment, we only have 0.05 mole to complete neutralization. Therefore, heat here is half as much. All right. Then, okay. But notice that the total solution volume differs. In the first case, we have 50 plus 50, right? So 100, the total of total number of volume in the first experiment is 100 cubic centimeters, while in the second was this experiment, the total volume is 75 cubic centimeters. All right. Okay, so I think we will use specific heat here. Yeah, we'll get the ratio. Okay, temperature rise formula. So delta T is directly proportional to the heat released per mass of solution. So we assume the density is equal to 1.0 gram per cubic centimeters. Okay, for the first experiment, let's assume it's 100 grams and change of temperature is 13. So that is QMC delta T. So assume assume 100 grams. This is 100 times C. Oh, what is C? A specific heat. That is 4.18, right? 4.18 joules per gram Kelvin. And then 13 degrees Celsius. Oh, we convert that to Kelvin. For the second experiment, heat is half, so that means Q over 2. That means the mass is half of it. Oh, nafawa. Okay. Okay. To make it clear. Okay, the volume of the first experiment is 100 cubic centimeters, right? So we assume that the mass of the first experiment is 100 grams. And for the second experiment, the volume is 75. So we assume that the mass is 75 75 grams. Okay. Then we get the ratio of this. So this is Q MC delta T2. We're interested in delta T2. Then we just get the ratio of them. Q over 2. So that is Q over 2. Get the ratio. So this is MC delta T over MC delta T2. Right. And then, okay, let me delete this. Okay. So delta T2 over delta T1 here is just equal to Q over 2 over Q. So this is Q over 100, 150, and 75. That would be 100 over 150. That is Q over 150 times the specific heat, Q over 100 times the specific heat. Then this cancels out, so we will have only 100 over 150, okay, which is just 2 over 3. Therefore here, delta T2, the temperature increase of the second experiment, is just equal to 2/3 of delta T1, and delta T1 is 13 degrees Celsius times 13. So delta T2, temperature increase of the second one, is 8. This is 2 times 13 divide 2, that is divide 3. That is 8.67 degrees Celsius. Kilojoules per mole. Okay. Do you have questions on this? You understand this? Okay, and then we go to number 4. Carbon dioxide are formed when 3 moles of chloroethene is mixed with 10 moles of oxygen and react as shown. So we were given here 2 moles of chloroethene C2H3Cl plus 5 moles of oxygen forms 4 moles of carbon dioxide plus water plus hydrochloric acid. So we find the number of moles of carbon dioxide formed, okay, when 3 moles of chloroethene is mixed with 10 moles of oxygen. Right. Okay, so we get the mole ratios from the equation. From the equation, we have 2 moles of chloroethene, this one, and 5 moles of oxygen. So that is 2:5, the mole ratio. Okay, and the actual amounts available are 3 moles of, okay, the actual amounts available are 3 moles of chloroethene and 10 moles of oxygen, but the required are okay. Okay, so let's calculate the required number of moles of required number of moles of oxygen for 3 moles of chloroethene. So the ratio here is 2:5. So we're given here 3 moles of chloroethene. So we just multiply this by the mole ratio. So 5 moles of oxygen is to 2 moles of chloroethene. That is 15 divided by 2, so 7.5. So the required number of moles of oxygen is 7.5 moles for 3 moles of chloroethene. Okay, but we have the available amount of oxygen here is 10 moles, so that means there is enough oxygen. Therefore, C2H3Cl or chloroethene is the limiting reactant. And now we can calculate the amount of carbon dioxide formed. Right. So from the given equation, we have 2 moles of chloroethene to form 4 moles of carbon dioxide. So the ratio is 2:4 for chloroethene to carbon dioxide. Okay. So we can reduce that to 1:2 or 1:2. Right. Okay. Okay, so we have 4 moles here, right? No, 2 moles. So 2 moles of carbon dioxide from the mole ratio. We multiply this by the number of moles of chloroethene. That is 3.0 moles. Okay, carbon dioxide. All right, so therefore this is the number of moles of carbon dioxide formed when 3 moles of chloroethene is mixed with 10 moles of oxygen. Or so you won't be confused, you just do like this. 3 moles of chloroethene, you multiply by the mole ratio. So that is 2 moles of carbon dioxide per 1 mole chloroethene. It's just the same. Let me just write down here. Boiling point, point trends depend on intermolecular forces. What are these intermolecular forces? The hydrogen bonding, dipole-dipole, London dispersion. So if it's hydrogen bond, the boiling point is greater than, it's the greatest, or greater than the dipole-dipole, and greater than London dispersion. And then next is the molecular mass. Heavier molecules, which means stronger London forces. And then for the branching of the compound or the elements. So branching reduces boiling point because there is less surface area. Okay, what do we have here? For the first option, what is this compound? CH3, CH2, CH2, CH3. What is that for option A? Is that, how many carbons are there? 1, 2, 3, 4, that is butane. And then 1, 2, 3, 4, 5, that is pentane. And then the other one is, okay, so that is butane, pentane, hexane. So boiling point increases with chain length, right? Because see, am I right? Yeah, boiling point increases with chain length. So therefore the order here should be, the greatest is hexane. So the boiling point of hexane here is greater than that of the pentane and butane. So this is C4, C5, C6. Okay, but then from the option here, they wrote butane is greater than, okay, butane is greater than pentane and hexane. And the question is arranged in order of decreasing. So option A is not the correct answer. And for option B, we have, what is this compound? 1, 2, 3, 4, 5, 6. That is hexane. 1, 2, 3, 4, 5. Okay, option B, we have N-hexane. Then we have, again, hexane, that is a straight chain alkane. And then we have 2-methyl pentane. Because it has 2 methyl here, right? 1, 2. And then for the other one, that is pentane, that's also pentane, neopentane. This is similar to the other problem we had in unit 1, neopentane. So we have straight, branch, this is branched, and this is branched. Okay, so that means the highly branched, the boiling point is less. So branching reduces boiling point. So that means the order of this should be N-hexane, greater than, N-hexane is greater than 2-methylpentane, greater than neopentane. So the order of this is decreasing, right? Yeah? Yeah, this one is decreasing. This is the option that is decreasing. So this should be the answer. Letter B. We can check option C. Option C is, C, we have CH3123 OH. So that one is alcohol. All of them are alcohol. 1, 2, 3. So the first one we have ethanol, and then propanol. We have 2 alcohol there, so that is propane attached to 1, 2, 1, 1, 2. Okay, 1, 2. We do diol, right? And then 1 is 1. We have 1, 2, 3. What's that? 1 alcohol. What's the name? Okay, so glycerol. What's glycerol? Okay, take note, for more OH groups, hydroxide groups, the stronger the H bonding, that means higher boiling point. So glycerol here is greater. It should be, glycerol is greater than propane and then greater than ethanol. So this is not the option. And for option D, we have, what is this? CH3Cl, what is that? And CH3Br, CH3I. What is that? Bromo, chloro, iodo. So this is halomethanes, which means that the boiling point increases with molar mass. So the molar mass here of CH3 iodo, the other one is greater. Iodine is greater than bromine and greater than chlorine. So this is the wrong order from okay, it should be iodine greater than bromine greater than chlorine, but from the book it's chlorine greater than bromine. Okay, so the answer is, should be letter B, the decreasing order. Okay, so for number 6, okay, we're given this reaction. Okay, all right, so chlorine is added to 2 cubic centimeters of a dilute solution of potassium iodide. The equation for the reaction between chlorine and iodide ion is this one. Which statement is correct? So for oxidation numbers, for chlorine here, the left side, Cl2 oxidation number, which is chlorine oxidation number, okay, Cl2, that is equal to 0 for the left side. And then on the right side, chloride, the oxidation number is -1. And for iodine, oxidation number, the left side, okay, this is for the left side, the oxidation number is -1, and then on the right side, oxidation number is 0. So chlorine here is reduced, while iodide is oxidized. So let's define the roles of each one here. The species that reduces chlorine here is the iodide ions, so they donate electrons, while the species that oxidizes iodide is the chlorine, which means it accepts electrons. So let's match the options here. So from the options, we have iodide ions oxidize chlorine, iodide ions reduce chlorine, chlorine reduces iodide ions, chlorine is neither oxidized nor reduced. So the answer here should be letter B. Iodide ions reduce chlorine.